So she will speak about parallel transport on Kendall shaped spaces.
Yes. So thank you for coming to this presentation. I represent the joint work with Nicolas, Guigui, and supervised by Alain, Trouvé, and Xavier, Pennec. So just to introduce a bit, the first goal of this work was to find efficient enough methods for computing parallel transport on Kendall shaped spaces. And so we had this existing method called Paul ladder method developed by Nicolas, Guigui, and Xavier, Pennec. But although we came to find some other methods based on integration, which at first look seemed very specific to Kendall shaped spaces. And the next questions was finally how generic could be these two methods. And so we compared the two on a numerical point of view, and although on a generalization point of view. So yeah. So what are the motivation of the work? So first, why parallel transport? Because it's really useful for extending learning method to manifold valued data. And especially as soon as you want to follow the evolution of the data along one parameter, then the right tool to use is parallel transport. But for example, for optimization procedure, what we require is also an efficient implementation of this parallel transport. And so we got interested in these Kendall shaped spaces, but it was also the occasion to experiment a bit more the Paul ladder method on a non-symmetric case, where we have exactly everything which is required from the method, that is the geodesics are known, but not the parallel transport. So why then Kendall shaped spaces? So they are used mainly in application for image analysis or biology. But although from the mathematical point of view, they are really interesting because they do carry a non-trivial differential geometry, for example, non-symmetric geometry, and also present some irregularities like singularities. So what we wanted to do for these spaces is also to be a method which clearly leverage the generic quotient structure to lead for a more generalization of the methods. So I just a bit about Kendall shaped spaces. So they are constructed in a way that we want to have a metric on shapes, which are encoded as configuration of points. And we want these shapes to be like the same from translation, rotation, and scaling point of view. So what we want is exactly a metric which is invariant to all this transformation. And it's constructed in two steps. So we have two quotient space. In fact, there are a first quotient space corresponding to taking out the action of translation and scaling, such that we obtain basically a sphere. That is the pre-shaped space. And on this sphere, we have like a natural metric inherited from the Euclidean rescale metric, which is invariant with respect to the action of rotations. And this allows to construct, so the final quotient space called shape space, which is has this manifold structure descending on the shape space, such that we obtain a manifold, but with singularity. And so now that we have this metric on shapes, we also have this Riemannian summation, which is descending to the base space, but away from the singularity. So as it is shown on the drawing. And this leads to like this idea that we want to have a bundle above, which is in correspondence to the bundle, to the tangent bundle of the base space. So that is exactly the idea of horizontal and vertical bundles. And this is this structure that we will use later for the two methods. So the vertical subspace at point X is defined just at the kernel of the differential of the submersion and the horizontal subspace, it's orthogonal complement, such that it is exactly identified with the tangent subspace of the base space. So now that we have this construction, there is a well-known result of O'Neill on Riemannian submersions, just telling that what we want is true. That is that the connection is also descending with this Riemannian submersion. And to be more exact, we have like this condition for the connection to be projected on the connection below. And this result is really interesting first because it means that the geodesics, as Jan said, are in correspondence with horizontal geodesics on the space above. But from the point of view of parallel transport, it's also really interesting because we have like an equivalent condition for the covariant derivative of vector field along a curve to vanish below, that it is the equivalent condition above is that the horizontal components of the above equivalent covariant derivative should vanish. So in other way, it should be this covariant derivative should be vertical. And so this is interesting from the point of view of the two methods. For ladder, it allows to have the geodesics in closed form and so the exponential. And then later on, all we need to do is to compute the logarithm using this exponential. And for the first method that I'm going to present right now, it's just like basically we will use this O'Neill results to put the condition we need for a vector field, a horizontal vector field, to be projected on the parallel transport. So for this, we need two things. We need for it to be horizontal, and that's the first condition showed on the board, which is divided in two conditions. So for it to be tangent, and then to be orthogonal to all the vertical subspace. And now that we have this horizontal vector field, then we need for it to project on the parallel transport. And this is the case if, as we saw before, the covariant derivative is vertical. And so this is really general, but the case of Kendall-shaped spaces is really easy to use because we have like on the first end, we have like an exact description or almost exact description of these horizontal and vertical bundles. And although the other thing is that the space above is just a sphere. So on the sphere, we know how to do everything. And especially we know the connection. So then there is a more descriptive formulation of these conditions for a vector field to be the parallel transport. So first condition second condition, sorry, could be rewritten as a differential equation. And for it to verify all the other conditions, then we need to have a more explicit description of this vertical condition. And in Kendall-shaped spaces, because it is the action of the rotations, we have that it is vertical if it is written as a skew symmetric matrix, sorry, as times the point, the base point. And this can be, so this wall condition can be rewritten as a solution of, a unique solution of the Sylvester equation. So at the end, we have to solve a differential equation together with Sylvester equations. So it's quite simple, and the method then is just to implement an integration scheme, right? On the other hand, we have this method, well-used method called ladder, which is mostly based on geodesics and the logarithm. So what we do is like to translate this vector, we build a small geodesic parallelograms, and we go step from step to the translated vector, and it converges when the number of steps goes to infinity. So we implemented the two methods in the Jumpstart library. So it's perfectly reproducible, and so you can use it if you want to. This is a representation of the method on some Kendall shape space, which is the one of triangles in dimension 3. So now the convergence properties. For this first method, integration method, as I said, we just have to use an integration scheme. So the order of the method is just the order of the scheme. So for example, with Runge-Kutta of order 4, the error is decreases in proportionally to 1 over n to the power of 4. But for the polar method, we already have this result saying that the method is of order 2. However, if the space is symmetric, it is of exact in just one step. That's why it's mostly used for symmetric spaces, because it's particularly adapted. So these experiences just translate the convergence properties, but in diagrams. So as we see in a symmetric case, so that is, for example, a Kendall shape space of dimension 2, then it is exact in just one step. But on a non-symmetric case, pole ladder is equivalent to a method of order 2, while the method of order 4 converges faster. So that is the comparison from the numerical point of view, let's say. But no, there are another question interesting us, that is how generic the methods are, and what happens if you want to generalize the methods to more generic spaces. So on Kendall shape spaces, the pole ladder converges with order 2, so integration is faster. But in terms of computational cost, it's a bit different, because the integration scheme grows proportionally with the order of the method, since we have to solve all the Sylvester equation at each step. Then we already know that this pole ladder method is quite generic, because it only uses the geodesics and the logarithm map. So for any space where we have, just a good implementation of the geodesic is sufficient, in fact. But for this integration method, it seems that it's really specific to Kendall shape spaces. But in fact, it just could work for any quotient manifold where we know in a quite usable way the vertical projection and the connection on the other space. So in this case, it was really easy, because the space above is just a sphere, and the vertical projection resulting from the action of the rotations is also quite descriptive. But we could think that with any manifold of this quotient manifold of this type, it could also work really well too. So that would be one of the direction we would like to go in for extending this work. So that is explore the genericity of the first method, so integration methods, and to see how we can extend the work to other manifolds, and so how the two methods could compare on other manifolds. So non-symmetric manifold would be better, because we already know that for symmetric manifold, like pole ladder, is already working well. And the other direction we would like to go in is to exploit this implementation for Kendall shape spaces to develop first example of new manifold learning methods for Kendall shape spaces. So we would like to extend manifold to extend learning method to manifold value data using this parallel transport. And another thing we would like to do, which is a bit different, is also to understand better. And I did not say so much about this, but to understand better the nature and the role of the singularities in candle-shaped spaces. So how does it influence our methods and so on. So that's it for this presentation. Here are some references. And so thank you for your attention, and thank you to all the team who worked on this paper.
Okay, thank you. So thank you very much. Do we have questions?
Just a remark, I don't know whether you mentioned that. So I have an explicit formula for Kendall for parallel transport on planar Kendall-shaped spaces.
Yeah.
So did you compare that to polar ladder?
Well, so this is the case where it is symmetric, right? This planar candle-shaped spaces, it is symmetric. So in this case, the polar ladder is exact. So I don't know if it's this answer.
No, I was saying there's an explicit formula for parallel transport on two-dimensional candle-shaped space.
Yeah, because everything is explicit, right? With
the polar iteration to do one step, you can write it in explicit form.
Yeah, is that the same? So is that the same as the explicit?
It has to be the same.
Okay.
Maybe it's not formulated exactly the same way, but it has to give the same result.
Yeah, more questions?
And do you have an idea which manifold you want to test this? You said you wanted to test it on new manifold. Do you have any ideas?
Yeah, so this first idea came although before after I talked with Jan, which has in fact the same kind of equation for the parallel transport. So that's why I was thinking that it could be generalized if it's the same. It could not be just by chance to have two cases with the same thing. But first step would be maybe to modify a bit candle-shaped spaces to such that this action scaling action could be modified a bit by using another way of scaling forms. So just not divide by the standard deviation, but maybe something or order 4. So modify a bit and see if the action is still quite easy to understand and to lead to quite explicit vertical projection.
You might think of infinite dimensional shape spaces as well. You have explicit for the elastic metrics. You have explicit forms for the vertical projection. Maybe you can try.
All right. Thanks.
Yes.
The integration of Kendall shape space. I was wondering how does this work in the logarithm of that, right?
No, so I mentioned this scheme just for this equation, which is just a classical differential equation.
Okay, so it's not, the solution is not constrained to it.
No.
Other questions?
The solution is, I'm not sure. This is solving both the geodesic and the part transport. So it is on the manifold.
That's which moment is this enforced? Like, on the manifold.
Because it's solved on the manifold. It's solving what is the next vector part transport on the manifold. Now the accuracy is depending on the precision that you use.
Each step is
It's actually a discrete it's solving the geodesic equation and the part transport equation in a discrete form.
Yeah, at each time your solution is again on this horizontal space, so that it projects well on the the tangent space.
Like, it is on the manifold, but the geodesic is approximated.
In fact, we also started with enforcing projector vector after each iteration. Because you're right, the iteration is extrinsic. We use a sum in the ambient state. But we tried to put the projection at each step, and it was not necessary because with not even a large n, the room complexity is precise enough so that it doesn't, the errors are very small. So projection was not necessary.
Okay, thank you. Maybe we stop for questions in the room, but I'd like to see if we have questions on this. No, no question. Okay, so let's thank again. Elodie.
And the next speaker will again be Benjamin Elster about what the diffusion means, and he